Hello and welcome back to Unit 6 full review guide for AP Calculus AB. But just a reminder, if you want any of these notes, check my bio. I have a link to a bunch of calculus resources for free, including all of these notes that you'll find here. So also another, advisory, I guess. I will not be doing it like my typical review videos, although I will discuss everything that the College Board wants you to know. It will be in a different order, right? Although I guess you could say it's like normal order. I just didn't organize it like I did only for this video. So, first things first is that the College Board wants you to know that if you have a rate, right, R prime is the rate of change of R. And we are adding up, accumulating this change, which is the area of R. Basically, the area of R, right, on between A and B of the rate is an accumulation of change. So what do I mean? If we take the area of R, that's giving us the net change of R over A comma B. So the area of capital R. The net change of R of X over A comma B is R of B minus R of A. That you need to know. So R of B minus R of A is this area underneath the rate. And how can we get this, right? And also, how do we know this is even true, right? This makes no sense. Maybe we're talking about work, and we might like to think this is force times displacement, but in reality, it's a lot more complicated and it can get dynamic. So how can we discuss this? Well, we'll start by approximating this change by creating rectangles. For example, if we have, x naught, x1, x2, x3, x4, x5 as our partition, then the area is f of x naught times x1 minus x naught plus f of x1 and so on and so forth, adding them up. You should know this pretty well, how to do this, like, you know, visually or maybe from a table, how to add these up and approximate, but I'll give you all the formulas that you need in just a second. All we're doing is we're taking this left point, f of x sub 1, or sorry, sub I. Let's say it's this left point. That's our height, all right? So we're going to take this height, we're going to multiply it by this distance to get the area of the rectangle, and we're going to sum that. That's all we're doing. So you need to know this formula is a left Riemann sum, but in this case, n is equal to 5. For a right Riemann sum, instead of taking this left point, we'll take f of x sub I, which is the right point. Um, Now you do need to know when a left Riemann sum and a right Riemann sum are under or over estimates. Now, clearly, a left Riemann sum is an underestimate for an increasing function, an overestimate for a decreasing function, and a right Riemann sum is an underestimate for a decreasing function and an overestimate for an increasing function. Um, that should be hopefully kind of easy to see. And note, overestimate means that it is the upper bound of that. That's the highest it could get. Not necessarily will it be greater, it could be equal to, right? Only in the case where it's like what, linear. No, or it is a rectangle, like it's constant. Now, following this train of thought, if the rate is positive, then the net change is positive. Um, this is pretty obvious, hopefully, right? What does increasing mean? Well, any 2 points in the interval, that is less has a lesser output. So of course, if the rate is positive, then the net change is positive, and the rate is negative means the net change is negative. So, since we said that this area was the net change, if the rate is positive, then the area under the rate is positive. And if the rate is negative, then the area under the rate is negative. But this doesn't just matter for a rate, since we could just let our rate describe, let's say, what we're going to define an antiderivative. In any case, the area under a function, the sign is determined completely by the sign of the function. And this will make more sense in just a bit. Now, we can also define area using geometry. You need to know your formulas. Hopefully, you know triangle and rectangle and trapezoid. So we can find this area of R by simply splitting this trapezoid, splitting this rectangle, and using our area formulas. This you do need to know, but if it does ask for an integral, which we'll talk about in a bit, you can always compute it using area. Now, what is the unit of area, which is the unit of the integral? It's the unit of the x-axis times the unit of y-axis. Again, this should make sense. Inches times inches is inches squared. Finally, what are our types of Riemann sums? Remember up here we talked about left and right Riemann sum? What are all the types? Left point Riemann sum, which is the left Riemann sum, is what we talked about already. Same with right Riemann sum. Midpoint Riemann sum is slightly different. Instead of considering the left point of any subinterval or the full right point of any subinterval, we're gonna take the midpoint. All right, so we have, let's say, little, you know, graph here, and we have this subinterval. But we're gonna do that. We're gonna consider the output at the midpoint here. So we're gonna go up, and we're just gonna take this midpoint here, call it a day. And the trapezoidal is just taking this here and from the subinterval, right, where we have here, what we're going to do is we're going to connect this from the left point to the right point, whatever, it's going to be some line that, and we're going to make a trapezoid, right? So it's an even better approximation. So this one specifically is typically better than a left or right point, and the midpoint is kind of the same. It doesn't like particularly make a difference. It just depends on how the College Board asks you, whether it is either of these four, you need to know how to do it from a table. So that's the more general formula, but you need to know, okay, left point, I take the left endpoints, right point, I take the right endpoints, the outputs, right? The outputs. Midpoint, I take the output of the middle, and trapezoidal is I average the outputs. So what are we talking about, right? Let's define everything. Okay. This is a more complicated definition that the College Board adds, but you're not going to be asked to reciprocate this or give it to them just like they've given it to you. Instead, probably what it is going to be what I'm going to show down here. But I'll quickly describe the definition. Assuming f of x is not necessarily defined on a comma b, right? We have some, we can extend it, but we have mostly defined, right? Almost everywhere except um, countably many discontinuities or where it's not defined. So what does this little thing mean? This is a tag. X sub I tagged is just some point in any general subinterval. So we're talking about subintervals here. I have a random subinterval. X sub I is a random x coordinate. It can be any x coordinate in that there, right? And I is just in the natural numbers, which can range all the way from here to the one right before b, which is n minus 1. And delta x sub I is just this width right here, x sub I plus 1 minus x sub I. Finally, the norm of delta x, which is the norm of the partition, which is this double absolute value delta x, something like that, is just the maximum of all the delta x sub i's. Now, the signed area between x equals a, x equals b, y equals 0, which is the x-axis, and y is equal to f of x, is defined to be the integral from a to b, which is defined to be the limit as the maximum of the subinterval's width or length approaches 0 of this sum, this Riemann sum, where we take the output at any x coordinate in our subinterval, right? Our tag is anywhere. We're taking the output here. We're considering this rectangle and we're adding them up along any subinterval as long as we consider the limit as the largest subinterval goes to 0. Any partition, as long as eventually all of the partitions go to 0. Now, if we do have that the limit exists, it is a Riemann integrable function. If f is a Riemann integrable function, then the integral can also just be expressed as this. This is a much simpler version that you should know. In fact, I expanded it out here that you should absolutely know. And how to remember is that you start at a, you add up I times delta x, right? I is just how many times you go over. Delta x is the width, so of course that makes sense. And delta x is just b minus a divided by n, how many n times we have. But remember this formula. It shows up, it's very useful. And the idea is the limit as n approaches infinity. Okay, this makes delta x go to 0. So that satisfies that part. And x sub I, this little tag, if it is a Riemann integrable, then for any x sub I, this works. So of course, it would just make sense to just take x sub I, right? Doesn't that satisfy being in the interval? And what is our delta x sub I? We can just take, since we said any partition, any subintervals, as long as the largest subinterval eventually goes to 0, we can just take this standard partition, right, of equal lengths, right? Maybe we have two and it's the midpoint. Maybe we trisect it, quadsect, I don't know. Now, since the function is Riemann integrable, any Riemann sum and its appropriate limit as n approaches infinity works. Left, right, midpoint, trapezoidal, any Riemann sum you can think of works as long as it's Riemann integrable. And in AP Calculus AB, I don't know of a single function that they would ask you that it's not Riemann integrable. So yeah, every function they give is Riemann integrable for the most part. Um, there might be some like infinite discontinuities, but that's more BC. But nonetheless, most of the functions are Riemann integrable, so you don't have to worry about that. Then we move on immediately to the first part of the fundamental theorem of calculus. If f is continuous on a comma x, right, then the derivative of the integral from a to x of f of t dt, f of t dt is just f, but we're using a different variable to not get confused, right? We're taking this area, right, this integral. If we take the derivative, it gives us f of x. It's like we can cancel this out and just take x and plug it in as our input. This is very important because you're going to see it all the time in FRQs. For example, we have a function that is this area function, right? This integral is, as if we have x as an input, it's an area function. I discussed it in my videos. If we take its derivative, we're just going to get the original function. So you should know that, all right? Sometimes it'll be asked implicitly, though. So here's an example. Find the integral from -3 to tangent of secant of x of 1 over u squared du. Differentiate it. Find the derivative of that. First, we're going to express it as a composition, right? So we have x and we have tangent of secant of x plugged into x, right? Next, we're going to use our chain rule. Since we have a composition, we could take the derivative of this, plug that in here, and take the derivative of that, multiply them. So we're going to have the derivative of the integral composed with this input times the derivative of the input. What is the derivative of this integral? Well, the fundamental theorem of calculus tells us this constant, by the way, doesn't matter. It can be any number. It tells us we just plug in the function at x. 1 over x composed with tangent of secant of x, right? That's what we have here. What's the derivative of tangent of secant of x? Hopefully, you know, using another chain rule, secant squared of secant of x times secant tangent. And of course, we can just plug in, tangent of secant of x for x squared. That's no issue. Now, here's an example straight from a past exam or practice, I can't remember. It gives the graph, right? And it says the graph of if a differentiable function f is given above. If h of x is the area function, right, from 0 to x of f of t dt. So this is f. We can consider this kind of to be t, I guess, and this is f of t. And if h just starts from 0 and it accumulates this area, which of the following is true? So it gives us, we're trying to compare h prime, and h double prime. Well, we'll start with h of 6, right? H of 6 is this area. But we said when the function is negative, its area is negative. So h of 6 is negative. What about h prime of 6? Well, first fundamental theorem of calculus, take the derivative, and this integral disappears. We just plug in x to our function, f of x. So h prime of 6 is f of 6, which we clearly see to be 0. So h of 6 is negative, h prime is 0. What is h double prime? Well, h prime is f, so h double prime is f prime. And if we look at 6, the function looks increasing, right? It looks like it has a positive slope here, which is its derivative. So the derivative of f is positive. So we have h is negative, h prime is 0, and h double prime is positive. That's an easy. A as our answer. Properties of definite integrals. Um, Most of them are actually shared with indefinite integrals, and we'll talk about why in a second. But and before you say anything, this B and A being switched wasn't intentional, but it's still same thing actually. Having B and A like this doesn't change the meaning. Although yes, it was a typo. So linearity, we can factor out a constant from the integral, and if we have the sum of two functions, we could just split the integral like this. Hopefully you're familiar with linearity by now. And of course, if C is between A and B, then in order to integrate from A to B, we can just add the areas. For example, if we want to integrate this yellow area, we can just split it into this purple and this green area. So intuitively, that should make pretty logical sense. It should be pretty easy to remember. And of course, if we want to switch the bounds of integration, we just put a negative sign. Let's say we're integrating from A to B, right, or A to B. If we want to integrate from B to A, we'll just flip the sign and do it with a negative sign in front. And we'll define an antiderivative now. A is an antiderivative of F over, I don't know, some interval, but that doesn't matter. If A prime is equal to F, pretty simple. A is an antiderivative if the derivative of A is F. Now, we'll look at this little sidetrack, right? Side note. Since by the first fundamental theorem of calculus, the function g of x is this area function, remember, a to x of f of t dt. And if we take this derivative, we get g prime is equal to f by the fundamental theorem. But this satisfies our definition of an antiderivative. So an area function from a constant number to a variable is an antiderivative of the function. Very important to know. This is setting up a very close connection already between the integral and the derivative, or more specifically, the antiderivative. So we can, as long as we have a to be a constant, right, we can technically compute the general antiderivative simply by finding a general formula for the area, which is already very interesting. And we'll finally tie it all together with the second part of the fundamental theorem of calculus, which allows us now to compute the definite integral with ease. The integral from a to b of f of x is capital F of x evaluated at b minus capital F of x evaluated at a, or capital F of b minus capital F of a. Now, capital F is, of course, an antiderivative. Another way you might want to see it, you might see this, not might want to. You might see it like this. We'll get to this notation in just a bit. But this is an evaluating, right? We evaluated at b minus evaluated at a. But instead of just writing it like the definite integral, we'll use the theorem to just take the indefinite integral. And the indefinite integral of f is a family of functions which differ by a constant, right? That's why we add a plus c, never forget that. And all of these functions, right, for whatever c, this is a derivative, sorry, its derivative is f. What do I mean? The indefinite integral of sine of x is negative cosine of x plus c, because the derivative of cosine of x plus c, right, any constant, the derivative of a constant is 0, so we can ignore it, is sine of x, which is what's inside the integral. So negative cosine of x, the derivative gives us sine of x, so we have that the integral of sine of x is negative cosine. Makes sense? Hopefully it does. So going back now, if we want to evaluate a definite integral, definite gives us the area, indefinite is this function, right? We can simply find the indefinite integral, right? Whatever that general form is, and plug that in at B and subtract it by plugging it in at A. Um, so again, now we see the connection between something completely unrelated, but I won't go off on a tangent in this video. You need to know all of these properties. Reverse power rule, linearity of anti-differentiation, right? Again, it shows up, right? Just like we had linearity of just integration, linearity of indefinite integration. The integral of 1 over x is the natural log of the absolute value of x, not just x, the absolute value. The integral of e of x is e of x plus a constant. The integral of sine of x is not cosine, but negative cosine. And the integral of cosine is sine. Remember, it's the opposite. And the integral of secant tangent is secant. And the integral of cosecant cotangent is negative cosecant. The integral of secant squared is tangent, and the integral of cosecant squared is negative cotangent. And the integral of f prime over f, although this won't directly be asked necessarily, the integral of f prime over f is the natural log of the absolute value of f plus c. Very useful. And these, you might have seen an integral table. These kind of show up. If we have any of these forms, right, we can just write it as one of the inverse trig functions, arcsine, arctan, or arcsecant. And we don't have arc cosine or arc cotangent or arc cosecant because really arcsine and arc cosine, their derivatives just differ by a -1. So, I mean, it literally doesn't matter. We could just take out the negative if we have it. Remember linearity. So we don't have to worry about that. We only have three to memorize. You don't need to memorize it though, as long as you know how to get there, although it can be asked, and I'll give you an example. Reverse chain rule, also known as use substitution. I don't teach or I don't go over use substitution. I do reverse chain rule because I guess it's better, but if you do use substitution, that's what this is. If we can find a way to express the integrand as g of x composed with u of x times the derivative of u, then we can just evaluate the integral of g of u of x, right? You may see this as the integral of g of u du, but remember it's actually like u of x is a function. So what you might see is u is equal to 3x, so du is equal to 3 dx, right? Which is weird, but in reality, all we're saying is du dx is equal to 3, and du dx is u prime of x. So we are showing that if we can find a u prime in here, and we have g of u, then we can just take that out. The u prime doesn't matter, and we just get a g of u. The u this time, du. It's almost as if the dx's cancel out, but they don't, they don't actually. So the integral of cosine of 3x plus 4. Well, if we're looking for our u of x to be the input, right? It's u is an input. So we're looking here, and if you need more practice, check out my reverse chain rule video. So we're looking at the input, we look at his derivative, that's 3. We want a 3 here. We don't have it, but we can just add it here as long as we divide by 3 outside. This only works because it's a constant at linearity. It's not like we can multiply sign and divide by sign outside the integral. That doesn't work. And what's our g of x, our function? It's just cosine, right? Our input's u, our derivative is u prime, and our function is cosine. So now reverse chain rule says we set it up exactly like we want to. Reverse chain rule says we can just express it like this. Take the integral of g of x and plug it in at u of x. What's the antiderivative of g? It's cosine. It's sine. We plug in sine of u of x is 3x plus 4. So it's 1/3 sine of 3x plus 4 plus c. Remember, if you need more in-depth practice, I have videos going over examples on how to use it. Finally, another one. These are the last two integrals before we're done with Unit 6. This is the definite integral. But remember, in order to solve a definite integral, before we might have had to use what, like a Riemann sum. Now we'll use the first fundamental theorem of calculus. We will anti-differentiate it and evaluate it at 3 minus evaluate it at 1. So our main focus is now solving this integral. Well, we'll express the denominator as x to the -2 and the numerator as 3x to the -1. So it should hopefully become clear x to the -2, x to the -1. It's almost as if one is the derivative of the other, which is true. If we let u of x be 3x to the -1, that's our input for e to the x, then the derivative is -3x to the -2 by power rule. And that means g of x is, which is our function, is e to the power of x. So now we can just anti-differentiate. Remember, we want to get a -3 here, so we'll divide by -3 out here. And now we have our u prime and our g of u, right? Now, don't forget this evaluated part. So now we can solve, we get this. we evaluated at 3 minus evaluated at 1, and we get this as our answer. Our final problem, right? Tying it all together. Here we need to do some algebra. We need to complete the square. So in order to do that, first, I don't like this negative. I always like to have a positive x squared. So I'm going to take out the negative. And I'm going to focus in on this x squared plus 8x. This 7 plus 7, we can get rid of it later. Well, if you know how to complete the square, then you know 8 is 2 times 4. So we want to get a 4 squared here and add it. How do we do that? We add 16, subtract 16, and of course this 7 is here. What is 7 minus 16? It's negative 9. What is this? It's x plus 4 squared. So we get 9 minus x plus 4 squared, right? This negative, now we can distribute it. Now, hopefully this gives you some idea of what we're going to do. We take out the 6 because I don't really see a use for it. And now it should immediately reveal itself what type of integral this is. Some constant squared minus some function squared. As long as we have the derivative of this function in the numerator, right, then we can use our inverse trig function. And yeah, what's the derivative of x plus 4? Well, it's just 1, right? It's a line. So yes, we do have this form up here that I was talking about. Remember these? Yeah, those. Now that we have those, we can use the arc sine one. Alternatively, if you don't know how, you can just use reverse chain rule or u substitution uh, and get to arc sine. But either way, if you memorize it or not, you should know that this is our function. We plug it in, divided by our constant 3. Of course, we have the 6, and don't forget the plus c, and it's arc sine of that. And that's our answer. So that was the comprehensive content review of Unit 6. Come back for Unit 8 coming up. Yes, I said Unit 8 because I'm going to skip ahead to Unit 8 and come back to Unit 7. Unit 7 will be the last unit I do for particular reasons that I'll discuss in my Unit 7 review video. So stay tuned for that and keep reviewing calculus. Good luck.